The third of Maxwell's equations is called Faraday's law of induction. And you'll recall here, although this can exist both in an integral form, which we have discussed, and a differential form, in this level of the course we only discuss the integral form. And this says that the integral of E dot ds, this is section 32.4, as vectors, and this is around a closed curve, is equal to minus d by dt, the time rate of change with the negative sign, of the integral of b dot d sigma. And this requires a little bit of explanation. This is not this is an open surface, and this surface is bounded by this curve. So if we have this curve here, here's a closed curve, C, and if we take the electric field and add it up all the way around this closed surface, take the electric field, dot it with ds, here's a little ds element, we take a little vector here of distance, dot it with whatever the electric field might be at that point, take the dot product of the two, add it up all the way around the circle, then what we'll get is the time rate of change, how rapidly the magnetic field is changing through this surface. What surface? Any surface that has its edges on this curve. So if we imagine a surface, it could be like a balloon or a piece of rubber stretched over this surface, or it could be like a soap bubble. That's a good way to think of it. And if we take this wire that the soap bubble is formed around, then in fact that wire will define this surface that is a soap film, and we can say how much magnetic field comes through this whole surface. There we must take the magnetic field and dot it with a little piece of area, d sigma, and take the dot product of those and add up and say how much is the magnetic field through this whole surface, how much is that changing. This is called, you recall, the flux through this surface. There's a negative sign here, which means that it opposes it. That means in particular that if a magnetic field comes through this loop of wire, it's going to generate a current around here. It's going to induce a current, and that's why it's called Faraday's law of induction. So we can take a loop of current in a magnetic field, here's a magnetic field, and take this current loop and move it and twist it around, and if the magnetic field flux through that loop changes, either because of its orientation or because of the strength of the magnetic field in any way, then it's going to make a current flow around here that follows from this voltage. The voltage is going to be the integral of E dot ds around this curve. So around this curve, the electric field is going to push the electrons and cause a current to flow. That current will create a magnetic field that opposes the original magnetic field that's creating it. This is called Lenz's law, that negative sign. And it's kind of like Murphy's law. When you try to do something, nature opposes your doing it. And of course, this says in a more powerful way that changing magnetic fields give rise to electric fields. This is something we'll come back to in our next chapter when we study electromagnetism. I might also mention a very important concept. If we take a loop of wire right here, we have to make this so that this slips around so this thing can rotate. And we put a magnetic field over this whole thing and let this turn by turning a crank or by letting a generator like a steam plant or nuclear plant turn this loop around. It will of course alter the magnetic field that goes through the center of the loop, and therefore it will create a voltage, and this is the way we create voltage, and it is by Faraday's law of induction that we're able to generate electric power. So Faraday's law is of incredible importance in allowing us to generate electrical power, and in particular generate voltage that passes through two wires and therefore allowing us to transmit energy from one place to another without moving mass by only generating the voltage difference between two wires.